So yeah, I'm hearing some static.
I think that's the probably like auto canceling on your audio, Daniel. So I suspect
Well,
that as long as
I
someone's
mean,
talking,
it,
it
it
should.
went away when Serena clicked mute.
Oh, okay. Well, then we should be fine. All right. Are we ready then?
So I'm gonna be. I always get nervous.
Yeah. Well, don't worry about it. We're nice here.
I'm sure
Um,
you're nice.
so welcome everyone to this week's Origin seminar. Before we get started, as a reminder, please mute yourself, and unless you're speaking, keep your camera off to conserve bandwidth. If you have any questions during the talk that absolutely cannot wait, so like clarification questions, you can put those into the chat and then I will ask the speaker. All right, and with that out of the way, I would like to welcome this week's Origin Seminar speaker, Dr. Daniel Carrera. Daniel got his PhD from Lund University in 2017, and he is currently a postdoctoral fellow at Iowa State. He does modeling of both super Earth formation and planetesimal formation, which is what he's going to be talking to us about today. So Daniel, the floor is yours.
Thanks, and thanks. I want to thank the organizers for giving me a chance to present my work, and thanks to everyone who's here for coming. So yeah, our story begins with a child how. We've also in this picture. It's one of the most important and gorgeous results from recent years. The idea that so many protoplanetary disks have these rings of dust around them. And it really is a very ubiquitous feature in protoplanetary disks. So we see these rings a lot, really, really often. And what I'm thinking about is I want to form planets. I want to see whether these rings can be the site for planet information. So let's take. I want to think about how these rings work. These rings point to the presence of asymmetric pressure bumps. Uh, solid particles in a disk drift in the direction of the pressure gradient, which typically means that they drift toward the star. Now imagine that you have a pretty large pressure bump somewhere in the disk that locally reduces and reverses the direction of the pressure gradient. So particles here would drift outward, not inward, and somewhere in between there will be a point of zero drift. It will be a place where particles feel no headwind, and that would be a particle trap. Now, before we continue, I want to emphasize that a particle trap is not needed for a ring to form. A small pressure bump, like the one that I've illustrated here, will still create a ring-like structure because all it needs to do is it needs to slow down particle drift. This works a little bit like a traffic jam. Like if you think of a traffic jam on the highway, typically the cars on the highway aren't stopped, they're still moving. A traffic jam is simply a localized overdensity of cars caused by a region of slow moving cars. And and a similar effect can still cause this kind of ring. That's going to come back later because because the hope of the experiment would be to investigate the effect of the pressure bump size, and we will look at some bumps that are most of the bumps we'll look at will be on the small side. So what do I want to do with them? I want to use those bumps to concentrate particles enough to trigger planet deformation by the extreme instability. Now, I'm not going to get into all the details of how the extreme instability works. All you need to know is that it's a hydrodynamic process that concentrates particles into filaments. So in this movie, the color scale is the particle surface density. And the idea is that instability collects particles into dense filaments, and if one of those overdensities crosses the Roche density, gravity takes over and the particles undergo gravitational collapse. And so from that point on, gravity and the gravitational instability takes the rest of the way from this fuzzy particle cloud to the planetesimal, the final asteroid or Kuiper Belt object. And the other thing that you need to know about the stream instability is that it's not automatic. It needs some critical dust to gas ratio for it to be effective, especially for small particle sizes. The smaller the particles, the more you need to concentrate particles before the SI even becomes an effective process. And so the idea is we're going to have a pressure bump that will collect particles together. Hopefully it will take us into the region where the SI is active. Then the SI will collect particles more into filaments to the point where gravity can take over, and then gravity will take us the rest of the way to planetesimals. So here's what I did. I ran simulations with a really, really long shearing bots. So I have shown, I have illustrated the size of a typical SI shearing bot for comparison. And it needs to be this large because I want to put in it a realistic pressure bump like the ones that we see in ALMA. So I put in so the bottom center at 50U, comparable to some of the outer rings in HL Tau. It has a width of about 12 AU. That's comparable to some of the rings that we see in HL Tau and other disks. The simulation begins with a realistic solar-like dust-to-gas ratio of 1%. Although it's not on the slide, I have realistic particle sizes of about 1 centimeter based on a reasonable disk model and fragmentation limited growth. And I'm just going to let it run and see whether that bump collects particles and can trigger planetesimals formation. And the other thing that I want to keep in mind is that we would like the pressure bump to be stable against the Rossby wave instability. I'm not going to get into details as to what the Rossby wave instability is. In honesty, I only half understand it. But the point is that if the pump is unstable, then it'll be disrupted and it might disappear before you actually get to form anything. So the best results that I could find, a best guide for what pump is stable or unstable came from On et al. So I have a really convenient neat formula that I'm using. And applying their formula to our disk model, here we have the width of the bump relative to the scale height of the disk. Anything above this line should be unstable. Anything below the line should be stable. So my fiducial run would be the largest pressure bump that is still small enough to be safe and to be stable against the wave instability. But just to test, I'm going to explore the parameter space and investigate other values as well, including one where the pressure bump is big enough to have a fully formed pressure trap. So it will be a place where the pressure gradient is 0. And here's the result. This is the result. This is the story. It works. The simulations do form planetesimals. The most interesting result here is the green curve. So that will be the fiducial run. So these are realistic centimeter-sized particles in a small pressure bump that is Rossby stable. Here we have the particle density as a function of time. And you can see that at some point, the density goes way above the Roche density, well inside the region where gravity is the dominant force. And I'll show you in a minute that it really forms self-gravitating, very distinct particle clumps. Not surprisingly, simulations that have even larger pressure bumps also form planetesimals, and they do so faster. The smallest bump kind of didn't really do anything. The only bit of bad news here is for the runs with millimeters of particles. So I said that based on our disk model, the probably reasonable particle size is in a meter, but of course, particle sizes are uncertain. So we also tested millimeter particles, and here we have the particle density for the maximum particle density for millimeters particles. And you can see it doesn't get anywhere near the Roche density. If you take that line and extrapolate for thousands of years, it still doesn't get anywhere near the Roche density. So it's looking difficult for millimeter particles. Now, for those who have to worry about perhaps the simulation might not have had enough resolution to resolve the fastest growing modes of the SI. So it's something that I'm looking into. I'm currently working on more simulations at high resolution to investigate those. But so far, the story is that for the smaller particles, it might be difficult. Now, let's focus on the good news then. Let's focus on what happens to similar particles on a reasonably small pressure bump. So I have a movie to show you. So let's play this. The top plot shows the gas density. So you see how the gas began flat and it gradually formed a pressure bump. We will come back to that point later. Plot here is the across the, well, this is not the entire bot. This is the interesting subset of oh, my bad, actually. The top two plots are the entire bots, and the bottom two plots are the interesting subset, the interesting slice where the planetesimals form. And the next two plots show the surface density of particles from two directions. So one is looking down on the disk and is looking to the side. And you can see all the self-gravitating particle clumps forming. And you can see how that happens. The simulation produces these dense filaments that are very characteristic of the stream stability. And when the filament crosses the pressure pump and goes through here, the filament density increases and it gets narrower, and where the filament crosses the Roche density and planetesimals begin to form. Here's the same thing again. Here I also added the headwind speed. So you can see the place where the headwind is smallest as a point of reference. Because there's no particle trap, the headwind is always positive. And you can see that the clumps form a little bit after that. If you
Daniel?
Yes?
We have a question from Andrea Zella, who asks what the units of your x-axis are. Are they years or orbits?
In the previous slide.
And on the previous slide, yeah.
Like a movie?
Mm-hmm. Yeah, this one.
Yeah, the previous slide.
So it's units of this one.
Correct one? This one. Yes, thank you.
That slide. X-axis on that slide. So that's units of inverse omega. So that's units of the orbital frequency. So one orbital period is about 2 pi inverse omega, and the orbital period at 50U is about 200 years or so.
Thank you.
Does that answer your question?
Yes.
So it's in units of the orbital frequency at 50U. In any case, and so here's a simulation for the much larger pressure pump that has an actual particle trap. And you can see this is the point where the actual trap is, where the headwind is 0. Then planetesimals form a little bit earlier. You can see that. So the detail structure is similar, a little bit different. There are fewer clumps. They're more massive, as you might expect, because they have to accumulate more strongly here. Now, next, I want to take a brief detour to retest the work of student, an undergrad at Iowa State, Andrew Thomas, who's working with me. So I need to take a step back and talk a little bit more about how we make that pressure bump. So we'll use neutrino relaxation, which is a very simple way to make a pressure bump form gradually. So I have a formula here. The idea is you have a target density, that's a Gaussian pressure bump with an amplitude of 0.2. And the gas density is initially flat, and the bump forms gradually on a time scale in the order of T ring 4. So you can think of this as sort of an e-folding time scale. So you can think of this physically as either a bump that gets reinforced regularly by a passing planet. So if a pressure bump is caused by a planet, then the reinforcement time scale will be approximate in the order of the orbital time scale. Or you can think of this as pseudo force, as the strength of the force that's creating the bump. So with a longer reinforcement time, the bump forms more slowly, meaning that you could think of that as a weaker force creating the bump. So what the student did is he's investigating what happens if the pressure bump is only weakly reinforced. And we're still working on this. We're currently writing the paper. We have most of the results, but it looks like a weakly reinforced clump is about just as good at making planetesimals as a strongly reinforced one. Might be less efficient. Some caveats that are coming on that. Here you see the particle density as a function of time, again, units of inverse omega. This is the bump that has a reinforcement time of 1 inverse omega, 10, and 100. The fact that the planetesimals form later is not interesting. Of course, they form later, the bump forms later. The reinforcement time is the time that it takes for the bump to form. What I think is more interesting is that the maximum particle density doesn't get quite as high. And that could be a hint that they might be less effective. But again, caveats, it's difficult to measure this accurately because of the way we treat gravity in the simulations. I'll show you more of that in a minute. The number of particle clumps or planetesimals that we get varies by simulation, but it doesn't seem to have any clear trend. So there's no reason to believe that a weakly reinforced clump will make fewer planetesimals or fewer particle clumps. Now, this is a bit of a weird plot, and I want to take a moment to think about this. This is the mass contained in clumps as a function of time. And we'll define that based on the particle density. So this is in code unit. This is in units where the Roche density is approximately equal to 45. So this cutoff corresponds to about 10 times the Roche density, and this is about 20 times the Roche density. You can see that doesn't actually matter really where you do the cutoff, which makes sense because the particle density spikes so quickly. It doesn't really matter where you draw the line here or here. But what I want you to notice is that the mass contained in clumps increases rapidly. Now, don't trust this too much. This is where it's worth a moment to understand how gravity is treated in these simulations. We can't actually do the falling body simulation with computed gravity between all particles. We basically have to use a Fourier transform, which means that gravity has effectively a grid size, and inside one grid, you basically can't resolve gravity anymore. And that means that particle clumps can't collapse all the way down the way they would in the real world. They stay puffy, and they can make it easy for them to gather particles. So much of this growth could be is probably due to the particle clumps accreting particles in a way that's not physical. Some of it would be due to new clumps forming. But what's weird about it, and as always when I show it to you, is that is that it's not obvious to me why that growth rate would be any different, any different for a weakly reinforced clump. You can see that it is. So focus just on the blue and the red. We can largely ignore the green because here the pressure bump hasn't fully formed yet. So of course it will form planetesimals more slowly. But over here, we're comparing two pressure bumps that are fully formed. The only difference is the reinforcement time. Why in the world will one of them have the planetesimals grow in mass more slowly than the other? So there might be a real effect here, something to do with the particle feedback affecting the pressure pump a little bit more. I mean, I should clarify that this is why we need reinforcement, is because if you don't reinforce the clump, the particles will destroy it. Just by conservation of angular momentum, particles drift because they exchange angular momentum with the gas. Where does that angular momentum go? The particles lose angular momentum by giving it to the gas. The gas will move and become disrupted. That's why you need to have some sort of reinforcement. So it's not unreasonable to think that a weaker force reinforcing the clump could have some ripple effect, but the effect is complicated by the fact that we can't resolve gravity properly. So I want to report this, and it's interesting, but I also need to put a little asterisk next to it. So in conclusion, we have good news. We've done simulations with a large shearing bots with a realistic pressure bump based on the ones that we observe, a realistic dose ratio, realistic particle sizes, and we see them produce planetesimals by the stream instability. So that's great, and that's really interesting. And furthermore, the bump doesn't even need to be very large. In particular, we do not need a particle trap for planetesimals to form. For millimeter-sized particles, we don't have good news. It's looking difficult, and the best answer I can give you is that it may not be possible for planetesimals to form for that size particle. And we have some tentative results that we're currently working on that suggest that weakly reinforced pressure pumps, also form planetesimals, possibly at lower efficiency. And we're still working on this. Work never ends. I'm currently working on more simulations, a high resolution of a million particles to really figure out whether they will form planetesimals or not. And I will get back to you soon, I hope. And we're finishing up a paper on the effect of bump reinforcement. Thank you all for listening, and I'll take your questions.
All right. Thank you so much, Daniel. If you have a question, you can either put it in the chat and I will read it, or you can use the raise hand feature and I will call on you. So, questions for Daniel. Enrique, please ask.
Yeah, hello. Hi, Daniel.
Hi.
Thanks for your talk. Very nice results. So I'm wondering what would happen if you did the same study at 10 AU or 1 AU, for example. Would the millimeter particles be able to form planetesimals? How would that difference in size of the particles change regarding their ability to form planetesimals?
Okay, if you keep the particle size the same, it will get harder because at 10 AU the gas density is higher, and that means that the Stokes numbers, the Stokes number is the particle stopping time. And that's what really determines the physics. And the Stokes number is also higher. But you shouldn't keep the particle size the same. Particle sizes change in the disk, and at 10 AU they should be fragmentation limited. So they should evolve in a way that mostly keeps the Stokes number at about the same once you get into the fragmentation limited region. So the particles shouldn't be that small anyway. But another thing that I want to say is that at 10 AU, it might be more difficult to make a pressure bump that has an amplitude as high as I had it here and still have it be Rossby wave stable. And that's a bit of a worry that I have about what happens at NAU. So in a sense, I did it at 50U in part because it was easier that way. So it is harder at 10.
Okay, thanks.
All right, Andrea.
Hi, Daniel.
Hi.
Hi, nice to see you. Thank you for the talk. I have a follow-up question, which in part you have answered. So, the capability to form these dense clumps depend on the Stokes number of the dust. And, do you have a prescription for, what is at what Stokes number you see these, or what is the dust to gas ratio? At what level of the dust to gas ratio you start to form these clumps? Is there a threshold that is radially independent? So if you want to generalize, moving out of the specific case of HL tau, where you assume a specific gas density, can you generalize, say, okay, if the Stokes number is above this, you see it, otherwise it's not, or a dust to gas ratio?
Yes and no. So the best threshold that I have is this plot that comes from my paper with Chao-Ching Yang in 2017. So here I wrote particle size. What that really is the Stokes number. So it matches the Stokes number against the dust to gas ratio. And if you're both aligned, then you will form particle clumps. But since we wrote this paper, I've begun to believe that the story is a little more complicated than that. And I'm going to go back to the movie to show you that. So, okay, right here, you can see here that even away from the pressure bomb, so I should clarify, all of this is in regions where the dust to gas ratio is below that critical line, the place where you will not expect the SI to be doing anything interesting. And while it is not forming self-gravitating particle clumps, you can see that filament structure, and that creates a little bit of complexity that isn't really captured by that plot. So I wish I could give you a simple answer, and I can't. I get simulations that produce this kind of criterion are based on small boxes that don't allow particles to make those long-term wide filaments. But a good starting point would be to say that filaments like this that can form at apparently any dust to gas ratio might locally double your dust to gas ratio. And after doubling, then you can ask whether that takes you above that critical line. So that critical line is the best approximation that I have to an answer. Does that answer your question?
Yes, thank you.
All right, and we have a general question from Joe Najita in the chat, who says, very interesting results. What is the scale height of the particle waves that form in the simulation? Do they help or hinder planetesimal formation?
Scale height of those particle waves. Mm-hmm. Oh, I should have kept track of that. I forget. So let's take a moment to see this as a bots. So the height of the bots is 0.4 h. So I need to remember how much I cut the bots by, because that's not the entire bot. It's actually, I believe that bots that I'm showing here is about half of the total height, because I went to zoom in per layer. So this is probably about 0.2 h. So that's probably about 0.1 h. But email me and I will give you a real answer. What's the second part of the question?
How do these particle waves help or hinder planet formation?
That's a good question. I don't see how they help working. I mean, I guess I'm so used to them because these waves are a common feature of streaming stability. It normally does that, and I guess I sort of got used to them. It's part of what creates that filament structure. So with my apologies, I can't think of a good answer to the question.
All right. I also have a question. So in your conclusions, you said that if you have centimeter-sized grains at a pressure bump, you can form planetesimals, but if you have millimeter-sized grains, you likely will not. So what is your preferred mechanism for getting millimeter-sized grains to centimeter-sized grains that does not involve particle traps?
Oh, I mean, at that sizes, we're talking about dust coagulation. So it's a question of how sticky the particles are, when collision speeds, fragmentation. So, like a dust trap. Well, I guess a dust trap will increase the low particle density, and that could help growth. But I mean, you have to ask that question to someone who actually works on dust stickiness and fragmentation. But I think that the turbulence and radial drift are bigger worries than the actual particle trap.
All right, so there's.
Sorry.
Oh, go ahead.
But from my estimates, for this model that we use, which is again meant to be a reasonable one, the 1 centimeter was the more reasonable particle size. We added 1 millimeter because we want to see what happens if a particles are smaller. But the 1 centimeter was the expected value from a back of the envelope calculation.
Okay, so there's not an issue with having centimeter-sized grains at these rates.
Well, if you see, there's an issue. If you change the disk model, you could change the answer. Like if you make a disk a little more turbulent, for example, that will make it the particles smaller. If we change the slope of the pressure gradient, then you can add more drift, which makes so in the case of drift limited growth, the particles will be smaller still. Unfortunately, we just don't know enough about the structure of disks to predict with confidence exactly what's the right particle size. That's why you need to test more than one. You know.
Yeah. Enrique, you have something to add?
Yeah, actually, I have another question if no one else wants to ask anything. So I saw from your simulations, I may be wrong, but I saw that for some simulations, the planetesimals seem to form before the pressure bump, and for some others, they seem to form after the pressure bump. Is that so? And,
yes.
And if so, what does that depend on? And what's the typical difference shift between the position where the planetesimals form and the pressure bump?
Yeah, so let's begin with this because it's one will be easy to understand. The simulation has a pressure bump big enough to create a region with 0 particle drift. So this dashed line here is an actual particle trap. The particle trap is not the place where planetesimals form because the streaming stability requires some headwind, requires particles to drift a little. It's just part of a process. The streaming stability is sort of a radial accumulation of particle drift. You have particles moving at different speeds and accumulating radially. So if there was no drift, there would be no planetesimals. So it was the reason that the point where you have the ideal rate of particle drift, where there is some drift, and yet particles are more slow enough that they can accumulate and trigger this high will happen a little bit earlier. So I think that's reasonable. The case that's a little hard to understand is the the more general case where you have a pressure pump that never stops particles. And what I think is happening here is that platetismal formation is a gradual process. It takes a few tens of omegas to go through the process. So if you look at that snapshot before anything happens, you can easily believe that the highest density is in fact at the point of lowest radial drift, and that does look a little bit brighter than the rest. But once that forms, that filament continues to drift. So it's going to take time for the filament to go through the whole process of getting denser and converting into planetesimals. And meanwhile, that the filament is drifting while that's happening. So by the time you actually get to the planetesimals, it has moved a little bit, so they form a little bit later. Does that make sense?
Yeah, I see. Yeah, that makes sense. That does make sense. Thanks. Yeah, that's interesting.
All right, Andrea.
Yeah, again, if there's someone else that asks question, they can. I have a question about a clarification about the thermodynamics. So in your hydro simulation, I assume you use an isothermal equation of state. Is that correct?
Yes.
So are you concerned about hydrodynamics in terms of collapse of this planetesimal? Do you think when you reach this high density, do you think the thermodynamics might become relevant, and perhaps no? Then you have to worry about cooling times and maybe if you cannot cool, you can actually not. To some extent, this reminds me a little bit of gravitational instabilities, where the fact you form a fragment doesn't necessarily mean that, depending on the cooling time, it might or might not collapse. So, are you worried about thermodynamics?
I hadn't thought about it until just now, but no, I'm not, because it's worth understanding that these clouds are very different formation. With star formation, you have an actual gas cloud. Gas feels pressure, and that's where you worry about temperature, because a hotter gas has more pressure pushing it outwards, acting against gravity. These particles in the disk are effectively so there's no pressure to hold them against gravity. Does that make sense?
Yeah, qualitatively, I think it makes sense. I wonder down to what kind of regime this qualitative understanding works. When you go to very high density, can we still use that assumption or not? Or to what level, the temperature, eventually the temperature will increase enough that the gas also, there is gas there, right? It's not that.
There is gas, but the gas is not the thing that's collapsing. In fact, the gas. So what's collapsing is the particle component, right, and the gas is present as a source of drag. Right. So I mean, I'm sure that the physics of collapse are going to be complicated, but it would be more analogous to a Gilbert cluster where you have, and so a Gilbert cluster has temperature, but it's not exactly the same as a pressure in the sense that we think of it for a star or for a gene's instability kind of problem. I mean, it's not exactly like a Gilbert cluster either, because these particles also feel gas drag. I just can't think of a better analogy. But the particles themselves don't have pressure. All they can do is interact gravitationally, collide with each other, and lose energy by drag. So there's no temperature support like there is in a gene's kind of problem.
Thank you.
All right, Drew.
Yeah, I promise I'm not a plant, but So if you look at like any of the maximum particle density plots, you see like the initial spike where it's like the particles collapsing to the midplane. But you don't really see that for like the millimeter sized particles. Is that because they aren't like why, like what's, I guess, the reason why they're consistently so low density and there's no like initial free fall to the midplane like you see for larger particles?
Millimeter particles will still free fall to the center. They just stop sooner. I mean, I guess it's just hard to see here to see in this plot. So small particles have a smaller Stokes number. They are more strongly coupled to the gas, so they take longer to sediment. They get stirred up more easily. So turbulence will stir them up and create a larger skull height, as you already know. This is one of the reasons why the simulations need larger boxes. Is that what you're asking?
Yeah, I was just curious. I didn't know if it was just a result of them being smaller that they're less dense.
No, it's not density. It's about how coupled the gas. So in the limit of a particle with zero size, it's perfectly coupled to the gas and just follows the gas wherever it goes. That would actually be called a colloid. If I give an analogy, we know what milk looks like. We think of milk as a liquid, but it's not. Milk actually has suspended particles in it. We just don't notice them because they're so small that they just follow the liquid everywhere it goes, and that is called a colloid. For everyone, this is Drew, is the speaker. If you have any questions about his work, you can ask him.
Thanks.
All right, Jake?
Yeah, I just wanted to follow up on Andrea's question, and it's more of a comment, really, which is that even though the solid particles themselves, their temperature won't contribute to whether or not they collapse, the degree of turbulence will, right? And so that's not something that the turbulence in these models is only induced by the streaming instability. But if there were some external form of turbulence like MRI or one of these other non-ideal MHD variants on the MRI, then perhaps the criterion for collapse would be affected. So you could think of the thermal motion of the gas, which then imparts energy onto the particles. You can sort of think of that, or sorry, not the thermal motion, the turbulent motion of the gas, which then imparts energy onto the particles. You could think of that as sort of the equivalent of a Jeans effect, if you will. But we are only including the effect of turbulence from the streaming instability itself.
That makes sense. Yes, I agree completely. I have nothing to add. Well said.
All right. Any final questions for Daniel? I am not seeing any. In that case, thank you so much for an excellent talk and an excellent discussion. And thank you all for coming. Hopefully we'll see you next week.
Yeah, take care.